you hear me? Yeah, you come see our clubhouse in a tree. We are kids on a mission to educate ourselves about the NASA vision. Come explore math and science, cause that's what makes our alliance. We are the Wildfire Club, we yearn to learn and want to see everything that we can be. So come join us on our journey. Don't you touch that dial, and welcome to the NASA White House.
Hey, that's cool. What is it?
It's this new game I bought. It uses batteries so I can play it at the pool. Yes, high score.
Can I play?
Yeah, here you go.
So you ready to go to Mr. E's pool?
Yeah, as soon as Bianca gets up here.
Whew, it's starting to rain, and it's thundering and lightning too.
Does this mean we can't go swimming?
I don't know, it doesn't look good.
Let's see if KSNN is reporting anything on the storm.
I'm Ted Toon with this Kids Science News Network Bulletin. The National Weather Service has issued a severe thunderstorm warning for the immediate listening area. Anyone outside should take shelter immediately, and no one should go to the pool right now. This storm is capable of heavy rain, dangerous lightning, and damaging winds. We have a report from our on-the-scene reporter, I Am Listening, who is coming to us live from Wattsville.
Ted, I'm on the western edge of town, and I can tell you that the storm is just about here. We are experiencing high winds and rain showers. From where I'm standing, I can see spectacular lightning. That one was close. Oh my, the power has gone out. Ted, if you can see behind me, the homes of Wattsville have all gone dark. Victims of the storm's tremendous electrical surge. Back to you.
Thanks, I Am, for that shocking report. We'll be back, so stay tuned to KSNN for the latest news on the storm. Unless, of course, your power is out, and then you can't see or hear me.
The lights are flickering on and off.
The storm's right over us.
Maybe we better get out of the treehouse and into our houses where it's safe.
Good idea. I'll see you later.
Our lights are working again.
I can't wait to go swimming in Mr. E's pool. Well, we can't. Mr. E tells me that his power is still out at his house across the street.
Is that his house right over there?
Yes. I wonder why the power is on in our treehouse, but out across the street. Well, we are the treehouse detectives. We've solved a lot of other problems, and we can solve this one.
What problem? It was just a lightning storm.
Now let's not jump to conclusions. We need to think about this scientifically.
Why do we have to use a scientific method every time?
Because it works. You know those scientific methods like observation?
Hypothesis, variables. Yeah, we got it.
Well, listen. If it doesn't work this time, then we'll never use it again. Like that will ever happen. You do know where we need to go to get started, don't you?
The problem board.
So what do we know? We know that we had a lightning storm last night. And we know the power was on before the storm.
We also know that the power is still off across the street.
We need to know if lightning can cause a power outage. And we need to know what else can cause power outages. And we also need to know why we have power in the treehouse, but not across the street.
I still think lightning caused the power outage.
Okay, let's make that our hypothesis. Lightning caused the power outage. But that still doesn't explain why we have power in the treehouse and not across the street. I'll go do a web search on lightning and see what I can find. While you're doing that, let's check our hypothesis.
How are we going to do that?
I don't know. Let's see if Dr. D will help us. Hi, Dr. D. Hi.
Hi, guys.
Can you tell us what lightning is?
Sure. Wait a minute, what brings this up?
Well, I was telling Kaylee and Jacob that the power is still out across the street, but it's still on in our treehouse. We're trying to figure out why.
Where are you going to start?
We came up with a hypothesis. We think that lightning caused a power outage.
It was a pretty big storm last night. How are you going to test your hypothesis?
We're not sure.
Well, to understand lightning, we first need to look at some basics. Let's rip up this paper. Now comb your hair briskly and then bring the comb down close to the paper.
Neat. do that?
The ancient Greeks noticed the same thing when they rubbed amber with wool.
Who's Amber?
Not who, but what? Amber's fossilized tree sap.
Oh, okay.
The amber picked up little objects like strands of fiber and hair, just like the comb picked up the paper. We say that the comb and the amber are electrically charged.
Can other objects do the same thing?
Sure, this balloon can pick up the paper too.
Wow. And it picks up other things too. Like this rice cereal and salt.
The balloon will also stick to the wall. It can also attract a stream of water. Whoa! If you rub the acrylic rod with the plastic bag, it'll do the same thing. Now, how do you know that the balloon was charged and not the paper?
Well, if an object is electrically charged, it should pick up objects like little pieces of paper or other such objects. Let's see. Nothing happened.
Very good. A charged object will pick up other neutral or uncharged objects, but an uncharged object won't. Let's do an experiment with some tape. Bring this bar around. Put some tape on the table. I'll pull it up real quickly. And watch this. It attracted the paper. It must be charged. Now let's try two pieces of tape, one on top of each other. Hold on to that, please. How can we tell if these are charged?
We need to do the paper scraps test to find out.
Well, let's try it. Yep, they're charged all right. Well, here's the experiment. Let's hang up the single piece of charged tape. Now we'll pull up the double tape. First the top piece.
It attracts the tape, just like before.
It's repelling the second tape. We haven't seen that before.
What conclusions can you make?
Well, if an object is charged, it attracts uncharged items, but it may attract or repel other charged items. Does that mean there are two types of charges?
That's right. Two types of charges are positive and negative. The top piece and the bottom piece have different charges. Now let's do this again. This time we'll take both pieces of tape in exactly the same way. So
They must have the same charge.
that's right. Will they attract or repel?
They repel. Let's see. If the charges are different, then they must attract. Let's find out.
All right, we use the two tapes again. Both have different charges. How about that? Look at this machine. It's called a Van de Graaff generator. Jacob, stand up on the stool if you would, and put your hands on top. I'm going to turn this machine on and transfer a lot of charge into you. It won't shock you, I promise.
Wow, his hair is really standing up.
Is it because all my hair is charged the same way and each strand is repelling or pushing away from the strand next to it?
That's right. In the beginning, your body was neutral. It had the same number of positive and negative charges. We call the positive charges protons and negative charges electrons. And we transfer an awful lot of negatively charged electrons into your body. What kind of charge would you have then?
Well, if the number of electrons and protons in his body were the same, then they would basically cancel each other out. And then if we added a lot of electrons, then I guess his body would be negatively charged.
That's right.
And I always thought you were the negative one.
Now, if we turn the thing on again, build up a huge charge on top, move the second ball closer to the first. Wow, it looks just like lightning. Now, what's going on there?
Well, the electrons are jumping from the Van de Graaff to the ball.
It looks more like a flash of light than a bunch of particles.
Well, I learned that you can't see electrons, so how can we see these electrons?
Well, you're right, electrons are too small to see. But as the electrons jump from the Van de Graaff to the ball, they heat up the air and cause it to glow. What you're seeing is the glowing air, not the moving electrons.
Is this how lightning works?
Yes, it's very similar.
So, Dr. D, do we get electricity from lightning?
Not quite. I'll tell you what. I'm going to line you up with a researcher from NASA Langley Research Center in Hampton, Virginia. His name is Bruce Fisher. He's done a lot of studies on lightning. I'll arrange for you to meet him at the Virginia Air and Space Center.
Great. Thanks, Dr. D.
So, let's get up and go. Bye, Dr. D.
Bye, guys.
Hi, Mr. Fisher. Dr. D said that you have studied lightning and could explain it to us.
Sure. I worked for several years on a research program at NASA Langley where we studied the effects of lightning on airplanes.
What is lightning and how does it work?
Do you understand about positive and negative charges?
Yes.
As a thunderstorm builds and matures, the charges tend to separate inside the storm. Typically, the positive charges go towards the top of the storm, and the negative charges go towards the bottom of the storm. Now, what's important to remember about positive and negative charges?
I know that opposite charges attract and like charges repel.
Exactly. What happens as the storm matures, you start to get an attraction between the negative charges at the bottom of the cloud and the positive charges on the ground. And eventually you'll get those two charges to meet. And when they do, there's a channel between them, between the positive and the negative. That's what we call a lightning bolt, and that is a cloud-to-ground lightning discharge.
Why doesn't the negative and positive charges attract each other in the cloud?
They can. In fact, 70% of all lightning which occurs in nature just occurs up in the clouds, what we call cloud-to-cloud lightning.
Does lightning ever hit the planes?
Absolutely. In fact, let me show you something here in the museum. Walk over this way. Now see the airplane over there? That's an F-106B Delta Dart, which is a two-seat fighter aircraft, and it was used by NASA Langley, where I work, for about 5 or 6 years to fly through thunderstorms to intentionally look for lightning strikes to aircraft. The airplane's been struck about 700 times by lightning. During that time, I sat in the back seat of the aircraft, and I was struck by lightning about 256 times during all of our research flights.
There's no way I go up in a plane during a lightning storm. What's it like to fly a plane through a storm?
The greatest worries that you have when you're flying through a thunderstorm is not the lightning, because we were looking for the lightning and the airplane was ready for that. What we were frightened of was the turbulence. It's a very rough ride inside of thunderstorms. This is a very rough riding aircraft, so they get bounced around and jiggled around a lot inside the cockpit of the aircraft. It's a very rough ride. The lightning was the fun part. You could see the lightning boom, the lightning flash, hit the nose boom of the aircraft. You'd see the lightning channel cause sparks where it was melting metal on the front of the airplane. You'd see the lightning channel flicker. Sometimes you'd hear it rumble if it was a big enough lightning flash. You'd see it sweep from the front of the airplane to the back of the airplane, a real light show, as if it was in slow motion. Only lasts about 1 second, but it seems it takes forever when you see it hit the aircraft. And all you would typically hear, because we're wearing headsets, would be just a snap in your ear, just a snap when the lightning would strike. But a lot of the lightning flashes, lightning strikes we never saw, because they all hit back up in the rear end of the airplane, from wingtip to wingtip or around the exhaust of the engine. So we'd have to come back afterwards and look at videotapes with the pilots and figure out where the lightning strikes hit us and when the lightning strikes hit us. Because most of them, we never knew we'd been hit. You might just hear a snap, and you might lose that snap and all the other noises that are going on inside the cockpit of the airplane. All the research that we did is being used to make commercial aircraft safer, to make fighter aircraft safer, and it's even being used to make the launches of the space shuttle safer so that they don't get involved with lightning when they're trying to go into orbit from the Kennedy Space Center.
Wow. Does electricity come from lightning?
Lightning is an electrical spark, but power and electricity and lightning are not quite the same thing.
Can lightning cause the power to go out?
Lightning can cause all sorts of unpleasant things to happen, including power outages. But I'm not an expert in power generation. I'm an aerospace engineer. What you should do is send an email to your local power company and see what they can tell you about power outages and power disturbances from lightning.
Okay, thanks for your help, Mr. Fisher.
You're welcome.
Bye.
Have a good day.
I'm rubbing this balloon on my arm to give it charge. Okay, that ought to be enough. Now let's see if we can move this can. Wow, pretty neat. You can see how to do this experiment and other experiments on static electricity at the NASA Wi-Fi's website at wifiles.larc.nasa.gov. Now that we've learned about static electricity and lightning, let's go back to our problem board. What do we know? We know that lightning isn't the same as the electricity we use in our homes. We've learned about positive and negative charges and how opposite charges attract and like charges repel. What else do we know?
Remember the email that I sent to the power company? Well, the response says that lightning can cause an outage either at the power source or somewhere between the power source and our home.
So maybe we should change our hypothesis to lightning hit the power source. But what is a power source?
Isn't it the place where they make the power? You know, where the power comes from?
Like a bunch of big batteries? I suppose we need to know what a power source is and how power gets to our homes. I guess that's the next part of our investigation.
So how's your research coming along?
Fine. We changed our hypothesis.
You have to revise your hypothesis sometimes. It's part of the scientific process. How does it read now?
We said that lightning hit the power source.
I see.
Your train set is really neat.
Well, thank you. Been working on it a long time. Just putting the finishing touches on it.
Can you turn it on, Dr. D?
Sure. That's funny. It was working before.
Well, is the train plugged in?
Let me check. Yeah, it's still plugged in. I'm really stumped.
So what's up? Can you think of some reasons why Dr. D's train set doesn't work? Why is the power out on one side of the street and not the other? Do you think that lightning caused a power outage? How can the treehouse detectives use scientific methods to solve the problem? Stay tuned. We'll have more next time.
So, Dr. D, PJ tells us that your train set's pretty cool and that you were having problems with it. Have you figured out what was wrong yet?
Not yet. But I'll bet if we work together as a group and check out the variables one at a time, we'll find the problem.
Okay.
What's a variable?
A variable is one specific thing that can affect or change the end result or the answer.
I've got an idea. I bet it's the wall outlet. There's no electricity there, nothing else will work.
Let's make that our first variable. How can we check out the wall outlet?
We can plug in something that we know works.
Exactly right. I've got a plasma ball we can use. Let's turn the lights down a little so we can see it better, and we'll plug it in over there to make sure that it's working.
Cool.
Now let's plug it into the same outlet the train setup uses.
It works fine. I guess you've eliminated one possible variable.
I'll check out a couple of other things later. By the way, how are you coming along with your electricity mystery?
Well, we still think lightning caused the power outage across the street from the treehouse.
We know that lightning doesn't cause electricity, but we're still not sure where it comes from. Can you tell us?
Well, electricity is electric charges flowing through the wires of a circuit. In a standard circuit, the charges are electrons. There are several ways to force the charges to flow. Do you know what some of them are?
Don't batteries produce electricity?
That's right. In fact, we can make our own battery out of lemons or other pieces of fruit.
A battery? From fruit?
Sure. A flashlight or the battery in your parents' car isn't made of lemons, but it works using the same principles.
Can you use a lemon to power something?
Let's see. I've got a little LCD clock. It normally works with a watch battery, about 1.5 volts. Hook together some lemons like this, and let's see what happens.
It's working.
That's amazing.
Can you think of another way to create electricity?
How about solar power?
That's called a solar cell, isn't it? I saw on TV that NASA uses solar cells to power satellites and even the International Space Station.
That's right. Look at this solar-powered bicyclist here. The brighter the light, the faster he pedals. So do you know how solar cells and batteries cause the charges to flow?
What do you mean?
Electricity doesn't appear out of nowhere. A very important law of physics says you can't get something for nothing. It takes work to push the charges through the wires, and the energy to do that work must come from someplace. With a solar cell, it uses the energy of the sun, and batteries use chemical energy. What other kinds of sources of electricity are there?
A power company is the source of electricity. It's easy to plug into our outlets and get power. But I guess I don't know how they produce it. Do they use a battery?
No, that's a good guess. The power company uses mechanical motion, however, to create electricity. Let me illustrate. Turn this crank and tell me what happens.
faster I turn the handle, the brighter the light bulb glows.
That's right. When you turn the handle, you're providing the energy to force the electrons to move through the wire. The motion of the charges through the wire is called a current. Now this time, turn the crank, keep your eyes closed, and tell me when something happens.
Wow, it's a lot easier to turn now. What happened?
I screwed the light bulb. It only takes work to turn the crank as long as you're lighting the bulb. We were only lighting one bulb. Let's add some more bulbs, see if it's harder to turn the crank. All right, go ahead.
Whoa, it's a lot harder now. I'm really having to work at this.
But Dr. D, obviously people don't turn the cranks in a power plant.
What other sources of energy could you use other than people power to turn the crank?
We can use wind power to turn the crank.
Well, wind power is used to create electricity, but it's not often used for large-scale power production.
I think the power plant in our town uses natural gas.
That's right. Power plants use coal, oil, natural gas, and even nuclear fission to provide the energy to create electricity. In each of these cases, the burning of coal, oil, natural gas, and the fission of uranium provides the heat to produce steam. The steam causes a turbine to spin, which turns the crank and the generator producing the electricity. It's just like our experiment, but with more power. But there's another natural process that can be used to provide the energy to create electricity. Do you know what it is?
Isn't it flowing water?
That's right. When water flows downhill, it has the energy to turn the turbine. One of the most interesting power projects in the United States is at Niagara Falls. Why don't you check it out?
Okay, I'll email them and see if we can talk to them about their facility.
Hi, I'm Joanne Wilmot, the New York Power Authority's Regional Manager for Community Relations here in Western New York. We got your email and understand you'd like to learn more about the Niagara Power Project and how it works. Well, let me show you around. Before we get started, do you know anything about the Niagara Power Project?
I know that it sits on the Niagara River between New York and Ontario.
That's right. The Niagara Power Project is the result of cooperation between the United States and Canada. As a matter of fact, the Canadian power plants are located directly across the river from ours. Both the United States and Canada have shared the waters of the Niagara River for many years, and both countries are firmly committed to preserving the beauty of Niagara Falls.
Niagara Falls is really beautiful. I visited once on summer vacation.
It sure is. And did you know that when the Niagara Project produced its first power back in 1961, it was the largest hydroelectric power plant in the Western world at that time? Today, it's still New York State's largest electricity generator, and here we have the capability to generate 2,400,000 kilowatts of electricity. That's enough to light 24 million 100-watt light bulbs at any one time. The low-cost power generated here also saves New York State's businesses and residents millions of dollars annually.
How is electricity made?
Here's how it works. The Niagara Power Project, located about 4.5 miles downstream from Niagara Falls, consists of two main facilities. The Robert Moses Niagara Power Plant with 13 generating units, and the Lewiston Pump Generating Plant with 12 pump turbine generating units. Between the two plants is a large forebay or open canal. It's almost 1 mile long and about 500 feet wide. Behind the Lewiston plant is a 1,900-acre reservoir, which is like a large bathtub, and that holds additional supplies of liquid fuel, about 20 billion gallons worth. Basically, water is diverted from the Niagara River up to 600,000 gallons a second and travels through two underground conduits or tunnels under the city of Niagara Falls and the surrounding towns to the project's forebay. From there, water flowing through the Robert Moses plant spins the turbines that power the generators, converting mechanical energy into electrical energy. At night, when electricity demand is low, the Lewiston units operate as pumps, carrying water from the forebay up to the plant's reservoir. Then, during the day, when electricity use increases, the Lewiston pumps reverse direction and become turbine generators, similar to those at the Robert Moses plant. The water then flows back into the forebay and is used again at the Robert Moses plant. Using the water twice to produce electricity allows us to increase our efficiency and production. You learned earlier that there are numerous ways to produce electricity using different fuels. Well, here at a hydroelectric project, we use water as our fuel. So hydroelectric power is one of the cleanest and environmentally friendly ways to produce electricity.
Is all the water in the river used to make power?
That's a very good question, and the answer is no. If all the water in the Niagara River was used for power production, there wouldn't be any going over Niagara Falls. And because the falls is such an international attraction, the United States and Canada signed a treaty in 1950. And that treaty regulates the amount of water that must flow over Niagara Falls at all times of the year. The treaty says that during the tourist season, 100,000 cubic feet per second must flow over Niagara Falls. A cubic foot is equal to about 7.5 gallons. So if we multiply that by 100,000 cubic feet per second, there is approximately 750,000 gallons of water per second flowing over Niagara Falls during the tourist season.
So after the power is made, where does it go?
The power generated here at the Niagara Project goes to a variety of customers. Much of it stays right here in Western New York for business and industry to use. Some also goes to residential customers, both here in Western New York as well as throughout New York State. And a small percentage of the power generated here at Niagara is sold to neighboring states.
Can you tell us what can cause a power outage?
Power outages can be caused by a number of factors. Some can simply be equipment failures. Other times, severe storms, either windstorms or in the northern climates, ice storms, can cause damage to power lines and thereby cause a power outage. Sometimes it's just our customers requiring and using more electricity than the power plant can generate. That'll overload the system and sometimes also cause a power outage.
Thanks for telling us about Niagara Falls.
Thanks so much for stopping by, and we'll see you later.
So you can either set this radio out in the sun or turn this crank on the side and it plays for hours.
Pretty neat. How does it do that?
Well, the solar power or the hand crank charges up the rechargeable battery that's inside of the radio.
Did you have it the other night when the power went out?
Yeah, it was really handy. I could listen to KSNN even though the electricity was out.
The people across the street could use it right now. What's that sound? Is it your radio? No, I think it's KSNN.
I'm Ted Toon, and this is KSNN. Last night's storm knocked out power for thousands of customers in Wattsville. Just moments ago, the power company reports that service has been restored to most of the area. I Am Listening is standing by. I am...
Ted, I'm in Wattsville with Mr. Eel Ectrick. Now, Mr. Ectrick, you still do not have power, is that right?
That is correct.
Does having no power make it harder for you, an electric eel, to stun and then eat your prey?
No. You see, it's my house that's without power. I, on the other fin, am fully capable of delivering up to 600 volts. Just like that.
Back to you, Ted.
That was I Am Listening with another supercharged report. In other news, a proposed major highway expansion through the Charles Schultz National Forest was vetoed by the president.
Let's get back to work and figure out why there's still no power across the street. What do we know? We know that there's no lightning damage at the power source.
Because if there was a problem at the power plant, the whole area would be without electricity.
We also know that there's no equipment damage and that power has been restored across the area. What do we need to know? We need to know why the power is out only across the street.
When we talked to Niagara Falls, they told us about how power travels in a circuit. So I think we need to know what a circuit is and how a circuit works.
Okay, so where do we go?
Let's go to houses across the street. That's where the power's out.
All right, I'll change our hypothesis to say that the problem is somewhere between the power source and the houses across the street. I'll type these notes into the computer. I think we're on the right track. We must be getting closer.
So, Dr. D, have you figured out what's wrong with your train yet?
No, I worked on it some more. I checked the electrical connections to make sure they were tight. The train is still not getting any electricity.
What are you gonna do now?
Well, I have some electrical test equipment on my workbench. I think I'll unplug the power unit, take it to my workbench tonight, and check it out. Hope this will bring us some conclusions.
Good luck.
So what's up? How will learning about the power plant help the treehouse detectives solve their case? Are they right to revise their hypothesis? What do you think is wrong with Dr. D's train? We'll have more on the next segment of The Case of the Electricity Mystery.
I did a web search on electricity and found some really interesting facts.
Like what?
Well, you know about Tesla or Alexander Volta?
I think I've heard of him.
I found a video clip about the history of electricity on the internet.
Let's watch it. Maybe we'll find some interesting facts.
And now, the history of electricity. Here's Dr. Textbook.
Hello. Maybe you think that one or two people discovered electricity. Well, actually, electricity is all around us. It occurs in nature. Oh! Very funny. An electric buzzer. Now, you probably heard some story about Ben Franklin flying his kite. Well, don't believe for 1 second that Mr. Franklin was standing out in a wet field with lightning raging about him, holding onto a brass key. No, he actually was standing in the distance, observing the kite, taking notes, and what he found out was that lightning is actually an electrical spark. Now, on to Alessandro Volta. Mr. Volta was the first man to build a battery, and he did this by taking small plates of copper and zinc and putting moist pieces of paper in between it. So, as an ode to Volta, I will take this 9-volt battery and stick it on my moist tongue. Oh! Not a very good idea. Well, Thomas Edison built a generator to make electrical current, but it actually was a man called Nikola Tesla who found out that by alternating the electrons in an electrical circuit was a better way to produce electricity, and this we call alternating current. And the first place this occurred was in Niagara Falls. Wait, there's more to learn.
This has been the history of electricity.
You know, studying electricity is really interesting.
I think if we're going to solve this problem, we need to learn more about electricity and how it comes into our homes.
I wonder how a circuit works.
Maybe we'll get a better understanding from tomorrow's classroom lesson.
We have a special guest with us here today to teach us some basics about electrical circuits. We have Mr. Rick Walker, who is an electrical engineer from NASA Langley Research Center.
How many people think electricity is mysterious? Why do you think electricity is so mysterious?
It's probably because we can't see it.
That's a pretty common answer, Jacob. Most people have a hard time understanding things they can't see. So to help us see how electricity works, we're going to use something that we all know about. Let's go outside and learn about the basic components of a circuit using a fire truck and water. Today we're with firefighters from the Fox Hill Company No. 5 in Hampton, Virginia. Hey guys.
Hi, Rick.
Let's say these guys were on the scene of a fire. What are some things that they would need to be able to put the fire out?
Water.
And a fire truck.
That's right, we'll need a fire truck filled with water. What else?
What about a fire hose?
All right, now how do the firefighters get the water to the fire?
They hook up the hose to the fire truck.
Right, we definitely have to have the hose hooked up to the truck. So, what we have here are the basic components of a circuit. They have a power source, they have conductors or wires, and a load.
What do you mean by a load?
In a circuit, a load is a device that converts electrical energy into some other form of energy. For example, in an electrical circuit, we use a light bulb to convert electricity into light. The power source is what supplies our circuit with the energy to do work. For example, a battery creates electrical pressure called voltage that will push electrons through the circuit. On the fire truck, a pump creates water pressure. The pressure will push the water out if there's a path for the water to flow. The water travels to the load, which is our water cannon. Okay guys, whenever you're ready.
All right.
Now, let's go inside and compare this to an electrical circuit. Who remembers what components we need to make up a simple circuit? PJ?
A power source, conductors, or the wires, and a load.
That's right. What we're going to do is use this battery as our power source, the wires as our conductors, and this lamp will be our load. If we connect them in the right order, the circuit will be closed and the light bulb will light. Basically what we have here is the battery creating an electrical potential called voltage, which is pushing the electrons through the wires, up to the light bulb, and back around to the other side of the battery. When this circuit's closed, the light bulb lights. It's important to remember here that the battery is not creating electricity, but merely pushing electrons around the circuit. So what would you call it if you disconnected one of the wires?
If it's called a closed circuit when the lamp is lit, then would it be called an open circuit when the lamp doesn't light?
That's right. For example, the lights in our room right now, we have a closed circuit. But if I was to go over to the wall and flip the switch, what would we have?
You created an open circuit.
Exactly. At home, you use devices like switches and circuit breakers and fuses to make open circuits.
The people at Niagara Falls told us that power is generated by water that flows under the falls.
That's cool. In my class, we watched the fire department demonstrate a simple circuit with their fire truck. It really helped me to understand how a circuit works.
So are all homes on one series circuit? Because if one house lost power, doesn't every house lose power?
Yeah, they're just like Christmas lights. If one goes out, they all go out.
I don't think that's how it works.
I'll bet it does. Why do you think all the houses are out across the street?
But every house in our town isn't without power. Our treehouse still has power. I don't think our neighborhood is on one simple circuit.
I think our house's circuits are complex too. When you turn off a light switch, the whole house doesn't go dark.
I think we need to go back to the problem board. We learned how power is generated at a power plant and how everything runs on a circuit.
We know that a simple circuit is made up of a power source, conductors, and a load.
And we know that our neighborhood does not run on a simple circuit.
I think we need to know a little more about these complex circuits.
Okay, where can we find some more information?
I have an idea. Let's see if anyone on the NASA Wi-Fi's Kids Club has done any research on electrical circuits.
Okay, I'll send them an email and check on our NASA Wi-Fi's website. Hey, I found it! A classroom in Montreal, Quebec did some experimentation with complex circuits.
Cool, let's dial them up.
Bonjour, mon nom est Alex Roberts, dans l'école Beacon Hill, 5e année avec Mr. Robin, Quebec, Canada. Hi, my name is Alex Roberts in Beacon Hill School, 5th grade with Mr. Robin, Quebec, Canada.
Hi, can you tell us more about your experiments with circuits?
We're making different types of circuits using D-cell batteries, light bulbs, battery holders, and wires.
What do you mean different types of circuits?
Our job was to experiment on different combinations of circuits and observe what happens. We made a hypothesis of what we thought would happen. One student made a light bulb really bright with 2 batteries and 1 bulb. Another student lit 2 bulbs with just 1 battery. He found out that if he unscrewed one of the bulbs, the other went out too. This is called a series circuit.
Aha! I was right. If one light bulb goes out, they all go out.
Well, our teacher asked us to try and design a circuit with more than one load, like a bulb buzzer or motor that will keep on working if we remove one of the loads. One student drew a diagram with the same numbers of bulbs and batteries and used more wires going to each bulb.
Did you try unscrewing one light bulb?
Yes, when we unscrewed one of the bulbs, the other stayed lit. It was almost like the electricity went around the unscrewed bulb to get to the other.
What? That can't be right.
How is that different from the series circuit you made?
In the series circuit, the electricity traveled in a circle through each bulb, but in a parallel circuit, it traveled to and around each bulb. Look at these 2 circuits. The first one is called a series circuit. It is basically a circle. When you remove one bulb, the flow of the electricity is interrupted. The second one is called a parallel circuit. The electricity goes to each resistor separately and bypasses the ones not connected. And that's the difference between parallel and series circuit. Our teacher said that we can make complex circuits by combining parallel and series circuit into one big circuit. That's what we're going to try next.
Okay, this is great information. Thanks for your help.
Au revoir, les amis.
Bye! Hey, Matthew, what are you doing?
I'm just playing with these Christmas tree lights. I guess these lights are wired up in a series circuit because when I take one light bulb out, they all go out.
But not all the lights go out. I have to take another light bulb in a different part of the strand to get the other lights to go out.
So is it a parallel circuit or a series circuit?
These lights are definitely a series circuit.
But the whole strand is a parallel circuit, 2 sets of 50.
I guess it's a combination of both. Each section is wired in a parallel, but the bulbs within each section are wired up in a series.
Hey look, another KSNM report's coming on.
I'm Ted Toon, and this is KSNM. Officials from the power company report that all major circuits appear to be working. KSNN's own I Am Listening is on the scene at one house still without power. I Am?
Ted, you could probably see me if my cameraman had remembered to bring fresh batteries for the lights. At the moment, I'm standing outside the home of a Mr. E. His neighborhood is the only one that has no power tonight. The power company reports, however, that all overhead lines that were damaged by the recent storm have been repaired. What is causing the blackout in Mr. E's neighborhood? We may never know. Back to you, Ted.
Thank you, I Am, for that electrifying account. I'll bet in next month's electric bill that the Treehouse detectives can solve this current case. Current! Get it?
If all the main circuits are working, then the problem must be pretty close to our neighborhood.
Maybe the problem is inside Mr. E's house.
What do you want to do, snoop around Mr. E's house when he's not there?
We can't do that. We don't even know what we're looking for.
So maybe we should figure out how our houses are wired first.
You mean in a parallel or series circuit?
Exactly. Let's ask Dr. D for help. Now we've learned all about series and parallel circuits, and we're ready to see how our houses are wired.
The model of a house right here. How can we tell whether it's wired in series or in parallel?
Well, we know that when something is wired in parallel, when one lamp burns out or is turned off, the rest of them stay on.
Not only that, but the lights that are still on don't change. They don't get lighter and they don't get dimmer.
Let's try it. Let's turn one of these lamps off and see what happens.
They must be in parallel because in series, all of the lights would have gone out when one was turned off.
Why is it important to have a house wired in parallel?
Well, it'd be really annoying if I was playing on the computer and my dad turned the lamp off and the computer shut off.
Or if I was in my room and my light got dimmer because someone else was turning lights on in the house.
Well, as more and more devices are turned on in the house, the number of charges flowing through the circuit increases. Each device gets just the current that it needs, but the current flowing in the supply wires must supply current to all the devices. If too many devices are turned on, the current in the supply wires is too great and the wires get hot. This is called an overload. The circuit breaker trips and turns the circuit off.
I guess the circuit breaker is in series with everything else. When it is turned off, we have an open circuit.
Why would you want everything in the circuit to turn off?
Because if the wires and the walls get too warm, then you'd have a fire on your hands.
That's right. Now, sometimes an appliance malfunctions and causes a short circuit. That basically means the two incoming wires touch. There's a huge current that runs through because it's bypassing the load. Now, when a short circuit occurs, what happens?
So the circuit breaker opens the circuit so no harm is done.
That's right, just like this. So when a circuit breaker is tripped, you have to first fix the problem, then turn the circuit breaker back on. Just like several wall outlets in a house are connected together and protected by a circuit breaker, so the houses in a neighborhood are also connected together in this parallel circuit and protected by a big circuit breaker.
So how many houses are in a circuit?
Could be as many as 4 or 5.
Does this mean if there's too much current going into a house in the circuit breaker opens the circuit?
That's right. When the circuit is open, all the houses go dark.
Wow, we may be onto something here. But what could cause too much current to go to the houses?
I guess the circuit breaker isn't working.
No, I think it's more of a problem with the wires running to the houses. Maybe there's a short circuit in the wires.
Good thinking.
Why didn't we think of this earlier?
Maybe because the electrical wires in our neighborhood are buried underground. That way, the short circuit could be hidden from view.
This could be tough. Hey, Dr. D, have you had any luck with your train?
Nope. I checked out the power unit on the workbench last night, and it is indeed working. This is really getting puzzling. Wait a minute. Talking about series and parallel circuits reminds me of something else to check on the train.
What's that?
Well, the pieces of track form a series circuit. If one of the lengths of track is not properly plugged in, we have an open circuit. The train won't work. I'll check on that later.
In the meantime, I think we should revise our hypothesis to there was an open circuit somewhere between the power source and the houses across the street.
Well, good luck on solving your mystery. It sounds like you're getting close.
So what's up? Why do you think the power is still off across the street? What would happen if your entire city was wired on one big series circuit? Is an open circuit keeping Dr. D's train from working? Do you think the Treehouse detectives are getting closer to solving the case? Stay tuned for the final installment of The Case of the Electricity Mystery.
So, we've revised our hypothesis to say something damaged the power lines in the area where the power is out.
Something? Boy, that could be anything.
Yes, but let's not give up. Remember, Dr. D says the answer could be right in front of us. Let's check out the problem board. Okay, we know there is a difference between parallel and series circuits. And we also know that rooms in our homes are wired in parallel circuits.
Houses in a neighborhood are connected together in parallel, much like the rooms in our houses.
We need to know if something can go wrong with power lines and cause an outage. Remember what Dr. D said about short circuits? We need to know if there is a short circuit across the street.
Oh look, a KSNN report. Maybe we'll get another clue.
Ted Toon here with this special report. We've just been informed that I Am Listening has a new clue in the mystery power outage story. I Am, are you there?
Ted, we've just been informed that authorities are on the lookout for someone named Public Damage. Power company officials feel that Public Damage is probably responsible for the power outage here in Mr. E's neighborhood. It is unknown at this time what Public Damage looks like or what his or her motives might be.
I Am? Are you there? We seem to have lost contact. Oh, wait.
Ted, this just in. I've fallen into a hole in Mr. E's yard. I'm covered with mud and getting very cold. Back to you.
Thanks, I Am. There you have it, ladies and gentlemen. Kids Science News Network will go to any depth to report on a story. And now we join our regularly scheduled program already in progress.
I don't get it. What is public damage?
Remember that email that we received from the power company?
Yes.
Well, they said that we could go along with the utility crew and see what they do. Maybe the crew could tell us more about public damage.
Good idea.
Let's get up and go. I'll set it up.
Hi, Catherine. Hi, Bianca. I'm Warren Walk with Dominion Power. I understand you want to learn a little bit more about what we do and about public damage.
Yes. What is public damage?
Public damage is when a person causes a power outage. It might be as far as a car hitting a utility pole, or somebody digging in their backyard hit an underground cable, or even vandalism.
So if there's public damage to a power line, it's your job to fix it.
Exactly. We have crews that will go out and restore service to the customer. Come on, let me show you some things. Do you know how power gets to your neighborhood?
Yes. We know that it is transmitted from the power plant to our homes.
Exactly. When the generator spins in the power plant, the voltage comes out at about 230,000 volts.
Isn't that a lot higher voltage than what is used in our homes?
Absolutely.
Then why does it have to be such high voltage at the power plant?
Electricity travels much easier over long distances at a higher voltage. The high voltage electricity travels through wires that string all across the area. Eventually, these high voltage power lines go into a fenced off area full of large metal boxes, fat wires, and other stuff. These areas are called substations. In a substation, the very high voltage electricity is changed into lower voltage electricity. Even though the voltage is lower, it is still too high for you to use in your home.
Is there another place where the voltage is even lower?
That's right, there is. It's in your neighborhood. If you look up on the power pole, you'll see a round gray, looks like a can. That's a transformer. They're called transformers because they transform the electricity to just the right voltage for your home. In other neighborhoods, the wires are underground. In that case, the transformer is a big green box.
What is the voltage used for our homes?
Eventually, the voltage is stepped down to 240 volts for your large appliances. That would be like your air conditioner and your clothes dryer. And then 120 volts, and that would run like your hair dryer or your microwave or your toaster.
Is there a way that we can measure how much energy is used in our homes?
Yes, there's a meter on the side of your house called a kilowatt hour meter.
What is a kilowatt hour?
A kilowatt hour is a measurement of energy. Kilo means 1,000, so that's 1,000 watts, a kilowatt. A toaster is a 1 kilowatt device. If it were running for 1 hour, it would use a kilowatt hour of energy. You can figure out how much energy an appliance will use. You just take the rating of the appliance in kilowatts, the time it is on continuously, and multiply it. If a microwave used 1 kilowatt of power per hour for 3 hours, that would equal 3 kilowatt hours.
If we had a 3 kilowatt device that ran for 1 hour, would it be the same amount of energy?
Yes, it would, and you can also figure out how much it would cost to run that appliance.
How do we do that?
Ask your parents to show you your utility bill. On the bill, it'll show what you're being charged per kilowatt hour. For example, let's say the charge per kilowatt hour is 5 cents. We have a toaster, a hairdryer, and a microwave. We'll say that each of these appliances is a 1 kilowatt device. How much would it cost to run these appliances for 2 hours?
Well, a 1 kilowatt appliance running for 2 hours would equal 2 kilowatt hours of energy. If there were 3 appliances, that would be a total of 6 kilowatt hours.
Right, so find the price. We would multiply kilowatt hours times the cents per kilowatt hour. That's 6 kilowatt hours times 5 cents per kilowatt hour, or 30 cents. And so by using a little math, you can calculate what each appliance in your home will cost to run.
You can learn more about calculating energy costs at the NASA Wi-Fi's website. Thanks for telling us about it. Hey, look over there. I wonder what that person's painting on the grass.
Oh, that's Mr. Utility. He provides a service to locate underground cable for people. Why don't you ask him about his job?
Great, we'll do that. Thanks for telling us what you do, Mr. Walk.
Sure, I'll see you later.
Bye. Bye-bye.
Hi, kids.
Hi, can we ask what are you doing?
Sure, I'm working lines on this property to let everyone know that there's an underground power line buried there. The homeowners had called us up because they planned on putting in a fence. They were afraid they were damaged some underground utilities.
I wonder what would happen if someone was putting up a fence and they didn't call you.
That could be a problem. Someone can easily damage an underground utility simply because they didn't know it was there.
Would that be considered public damage?
Yes, it sure would.
But Mr. E doesn't have any painted lines in his yard, and he just finished putting up a fence, and his house is without power.
I don't remember seeing any lines in his yard either.
Let me check my list. No, I don't see a Mr. E on my list. And you say he's without power?
Yes, in fact, several houses are without power.
Jim to repair crew.
This is a repair crew. Go ahead.
We've got a homeowner here who has put in a fence. He didn't contact us, and I think we got a power break here.
Maybe there's public damage to the underground line.
We've had a report of an outage at several houses. We'll check it out. Thank you.
Hey, kids, what's happening?
Mr. E, did you call Mr. Utility to find out where your underground power lines were before you started putting up your fence?
What do you mean?
Mr. E, you should have called us. I could have easily shown you where the underground power line was, and you could have prevented this power outage.
Oh, man, if I'd have known I was supposed to call you, I would have.
Doesn't Mr. E look kind of familiar?
Hey, man, next time I promise to give you a call, okay?
Mr. E, my crews will make repairs and we'll get the lights back on. See you later, Treehouse Detectives.
Bye.
At first, we thought it was lightning that caused the power outage.
We tested the hypothesis and revised it several times. Eventually, we found a short circuit in Mr. E's house.
Good work, guys. Hey, Dr. D, did you check the train tracks to make sure all the connections were connected properly?
Yes, I did. I pushed them all in carefully, and then I checked the connection with an electrical meter to make sure there wasn't an open circuit. Everything checked out just fine, but it's still not working. I even took the engine to a friend's house to find it on his track, and it worked as well. This is really frustrating.
I bet with our experience in the electrical mystery, we could help you solve your train problem. There's so many things that can go wrong with your train, so we have to be sure to examine the variables one at a time.
Let's use the causes of electrical outage to help us.
Well, we know that your problem wasn't the storm because you still have power in your wall outlet, and I don't think it was an inside storm.
And you've checked the equipment, both the train and the power unit. And you've checked the track itself to make sure it was a complete circuit.
I wonder if public damage could be a problem. But who could cause damage and to what?
Well, wait a minute. What's Bernie doing? What do you know? Look at this. An open circuit at the extension cord. And it's wired in series with everything else. Nothing else is going to work.
Good thing it's not a short circuit, or else we'd all be in the dark.
But if your extension cord was bad, then how did you get the power unit to work when you checked it?
That's because I unplugged it from the extension cord and plugged it into my workbench. I didn't even consider the extension cord. When I plugged the power unit in someplace else, I changed one of the variables without even thinking about it.
Just like we didn't even consider the underground cables at first.
Let's plug it into a good extension cord and try it. Here goes. Yay! Scientists and even retired scientists need to make sure they don't assume anything.
We always need to keep our eyes open all the time.
That's right. You can find the clue in the most unlikely circumstances, even in a slobbering St. Bernard.
Come on, let's go! Yeah!
The NASA Y-Files is made possible through the generous support of SeaWorld and Busch Gardens and the NASA Langley Research Center's Aerospace Vehicle Systems Technology Program Office.